Everything we have learned about two-dimensional vectors also apply to higher dimensional vectors, except visualizing vector applications like multiplication and addition gets difficult. So let me start with a definition first here. So any vector with n dimensions is a column of real number. It's a column of real number x1, x2, dot 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 xn inside a column bracket. So here x1, x2, dot 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 xn, they belong to the real number set, and they are also known as the elements or the component or the components of the vector. So for example, 9, 8, 1, this is a three-dimensional vector. 1, 2, 3, 4, 5. This is a five-dimensional vector with elements 1, 2, 3, 4, 5. An n-dimensional zero vector is a vector where all elements are zero. So let me draw this. So let this be a zero vector of n dimensions. So this vector will have zeros, n zeros stacked on top of each other. So you will have n zeros here. So in the last lectures, we talked about representing two-dimensional vector in the xy plane. And this xy plane is also called the two-dimensional Euclidean plane. So let me actually write it down. It's called the two-dimensional Euclidean plane. So more formally, a two-dimensional Euclidean plane is denoted by R2. So it's denoted by a bold R with a superscript 2, and it's defined as the set of all two-dimensional vectors. So all this, this weird looking mathematical statement says that the two-dimensional Euclidean space, that is R square, consists of all possible pairs of numbers x1, x2, where both x1 and x2 are real numbers. All right. So now there is nothing quite unique or very important about this number 2 here. And using the same logic in the same vein, we can define an n-dimensional Euclidean space. All right. So let's define an n-dimensional Euclidean space. And we can define an n-dimensional Euclidean space just the way we defined a two-dimensional Euclidean space. So an n-dimensional Euclidean space would be represented by Rn, and it will be the set of all vectors that have n elements such that all the elements of that vector belong to the real numbers set. All right. Okay, so let's discuss some vector operations for higher dimensions. So two vectors, let's say u is equal to u1, u2, un, and another vector v is equal to v1, v2, vk. So they are equal if and only if k equal to n, that is the number of elements in u and v have to be equal, and and both the conditions have to be true. So this has to be true, and the next condition that has to be true is u1 has to be equal to v1, u2 has to be equal to v2, and un has to be equal to vn. All right, so basically the respective elements of both the vectors u and v have to be equal. um, let's talk about addition. So addition of two vectors in higher dimension is allowed only if the two vectors have the same number of dimensions. And also addition works in the same way as for a two-dimensional vector. So let's say if u is x1, x2, xn, and v is y1, y2, yn. So u plus v will be x1 plus y1, x2 plus y2, and so on and so forth. Scalar multiplication also works in a very similar fashion as is the case for a two-dimensional vector. So let's say C be a scalar. So C into U, vector U, will be C into x1, C into x2, dot dot dot, and C into xn. So basically we are multiplying every element of the vector U with the scalar C. The additive inverse of a vector u is a vector minus u, right? This is what we have seen. So let me define a vector u as u1, u2, un. So the additive inverse, define it, write it down. The additive inverse of u will be minus u. And what is minus u? Minus u is nothing but the scalar minus 1 multiplied by u. So that will be minus u1 minus u2 minus un. And you can get it, right? Why it's called the additive inverse. So if you add u plus minus u, right, what you get is the zero vector, right? Okay. All right, so that's all I have to discuss in this lecture. In the next lecture, we will talk about linear combination of vectors.